Hello everyone and welcome to lecture today. So today what we're going to be going over is a test for convergence of specific infinite series. So just like for improper integrals, we don't always want to actually evaluate the integral because the function might be very complicated. We just want to know whether or not the integral of that function converges or not, the improper integral. So we have this exact same thing that we want to be able to do for series. In general, we could have a very complicated looking series. In general, for series, it's actually more difficult, generally speaking, to figure out what that series is going to converge to exactly. So it's actually even more important for us to develop very specific tests that, given a complicated series, we can use to determine whether it's going to converge or not. And just like before, so for like the direct comparison theorem and the limit comparison theorem for improper integrals, these tests are only going to tell us whether or not the series converges or not. These tests are not going to give us the actual value of the series. But the first big important test that I think we should go over, we need to go over, I think first, is the integral test. And this is going to be basically comparing a given series to a similar improper integral and essentially using the convergence of the improper integral to give us information about whether or not the series itself is going to converge. So what I want to do is start by writing down the test itself in its entirety, and then cover a number of different examples on how to apply the test, and also what can be said using the test as well about how well you're actually approximating the actual series, because we can use this test to approximate the value of the series, but we can't use it to find the actual value of the series. So that's a very important point to make. So the theorem itself is stated in the following way. Let AK be a sequence and specifically it's an explicit sequence of positive terms so specifically we have that AK is equal to some function of the k, the kth term of the sequence, and this explicit function f is positive, continuous, and decreasing. So it's continuous, positive, and decreasing. And if so, this is the case, then the theorem says that the series of the AKs and the integral So the improper integral of the function f both converge or they both diverge. And that's it. This is the integral test. It's basically saying that given a series that's in explicit form and comes from some function f, where f is continuous, positive, and decreasing, the series itself has to do whatever the improper integral of that function f is doing. And this is the basis of this theorem. It's exactly what this theorem is saying. So throughout this lecture, I'm going to go through and show you a couple examples of this. I'll justify this statement, and then I'll show how we can actually kind of use this in a more advanced way to actually approximate what the value of this infinite series is. Now, I want to really emphasize again that the value of this improper integral is always going to be different from this infinite series right here. Right? So this is a very important thing that I want to emphasize. A big confusion that students will initially have sometimes with this theorem is they'll think that the series itself has to be equal to the improper integral, and this is not true. These two quantities, the series and the improper integral, are completely different values. And just because we know the improper integral doesn't necessarily mean we know the series, or what the value of the series is. However, this test is basically telling us that if the improper integral converges, and we can apply this test, then the series must converge, and vice versa. If the improper integral diverges, then the series must diverge as well. So it's a test that tells us whether or not this infinite series is going to converge or diverge by looking at the improper integral of the function that is generating this series. That being said, by the end of the lecture, we will have a very nice method of actually estimating how well the nth partial sum is estimating the actual value of the series. So one of the neat results that we'll show is that if we truncate this infinite series and obtain a certain partial sum, so we stop the series at a certain value and we use that value to estimate the series, the improper integral is going to give us a nice way of estimating the error in this approximation of the series. So what I'm going to do is start with the following example, and essentially this is going to be, I'm going to hold off on proving the integral test, and I will a little bit later on show you a proof and a visual justification of why the integral test is working the way it does. But I want to go over probably one of the most important examples in series for right now, and that's the example of what's called the harmonic series. I introduced this in the previous lecture. And the harmonic series is a divergent series. I made this claim in the previous lecture, and I want to go over a proof. I'm going to go over two proofs. The first one will be a direct proof, and this proof is a little bit longer than the proof using the integral test. So the direct proof for this involves looking at the nth partial sum of this series. So we know that the nth partial sum, Sn, is equal to the summation from k equals 1 to n of 1 over k, which is the same thing as 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 all the way up to 1/16 and this just continues all the way up to plus 1 over whatever that value n is, the value of n. And hopefully you can see that one of the things that we can do is group these terms in a very specific way. So if I group these terms between the powers of 2 So if I group these terms and I use powers of 2 as my divider here, so basically I group 2 to the 1 is this 1/2 term right here, and then we have 1/3 plus 1/4, which is 2 to the power 2, and we have 1/5, 1/6, 1/7, all the way up to 2 to the power 3, which is 1/8. So I'm grouping these terms together, then 1/9, 1/10, and so on and so forth, up to 1/16. What I want you to notice is that each one of these terms, right, 1/3 plus 1/4, is greater than 1/4 plus 1/4, because 1/4 is smaller than 1/3. So this entire term right here is greater than 1/4 plus 1/4, which is equal to 1/2. Same thing here. This term right here is greater than 1/8 plus 1/8 plus 1/8 plus 1/8, or 4/8, which is also equal to 1/2. This term right here is greater than 8 over 16, which is again equal to 1/2. So noticing this and taking the limit as n goes to infinity, specifically noticing that for any value m, s, the 2 to the mth partial sum, we compute the partial sum for a value of n equal to 2 to the m, this partial sum is going to be strictly greater than m times 1/2. In the limit as m goes to infinity, because m is going to infinity, this partial sequence of partial sums, s 2 to the m, also has to go to infinity. So therefore, the harmonic series has to diverge. And this is, I think, a very clever, very neat method of proving this. That being said, this is not always going to be possible to do, setting up inequalities like this. And with the integral test that I wrote down before, we actually have a much simpler method of proving this. And this is going to rely on one of the very special comparison functions that we talked about before. So specifically, if we look at the improper integral of the function that's generating this series, right? This infinite series, and I'll call this proof method 2, not an example. So this infinite series is generated, the AKs are generated by the function f of x is equal to 1 over x. Right, this is the function for which each of the terms ak is equal to f of k. So instead of looking at this series, what we're going to do is look at the improper integral from 1 to infinity of this function f of x. And this improper integral is an improper integral of the form integral from 1 to infinity of 1 over x to the alpha, where alpha is just equal to 1. And we know from the example, one of the first examples that I did on the integral direct comparison test lecture, this diverges. And this is easy to show if you kind of go through and do this improper integral. You're going to get the antiderivative is the natural log of x. And when you take the limit of this as b goes to infinity, this is going to end up being positive infinity. So it's going to diverge. But then, therefore, by the integral test, the sum of 1 over k from k equals 1 to infinity also must diverge. And this is the second way of going through and proving that the harmonic series has to diverge. So for another example, I'm going to kind of work off of this harmonic series example, and I'm going to consider the more general form of a harmonic series, which is called a p-series. This is going to be really, really important to us, especially when we get to the next convergence test, which is going to be the direct comparison theorem and the limit comparison theorem, but for series. That's going to be the topic of our next lecture video. So the p-series is going to be very, very important because it's a relatively simple looking series that we can use to compare to more complicated looking series. So this is why the p-series is going to be a very important series. And this is just, right, 1 plus 1 over 2 to the p plus 1 over 3 to the p, and so on and so forth all the way to infinity. And we just proved that the harmonic series, or the p-series when p equals 1, diverges. And you can ask a very good question, which is, for what values of p does a p-series converge, and for what values of p does a p-series diverge? And the answer to this question is to go through and do the integral test on it. So the integral test here is we have ak is going to be 1 over k to the p, which means that the function here, function of k, that is kind of generating this, the function of x that is generating this terms, all of the terms in this series, is going to be 1 over x to the p, which is just like the function 1 over x, a positive, decreasing, continuous function. And this is why we can use this in the integral test. So if we look at the integral of 1 over x to the p from 1 to infinity, with respect to x, you'll remember the result from a few lectures ago where we considered integrals of the form 1 over x to the alpha. And sure enough, this integral ends up being converging only when this exponent is strictly greater than 1. So, it diverges if p is less than or equal to 1, between 0 and 1, and it converges if p is greater than 1. So because of this, by the integral test, the p-series converges when p is greater than 1 and diverges otherwise. So this is going to be a super important series for us, and this right here is just kind of a proof that the p-series converges when p is greater than 1 and diverges when p is less than 1. So for just example, if you write down the infinite series 1 over k to the 3/2 from k equals 1 to infinity, this is going to converge. This is the series 1 plus 1 over 2 to the 3/2 plus 1 over 3 to the 3/2, and so on and so forth all the way to infinity. This converges because p is greater than 1, but this series from k equals 1 to infinity of 1 over k to the 1/2, which is the infinite series 1 plus 1 over 2 to the 1/2 plus 1 over 3 to the 1/2, and so on and so forth to infinity. This series diverges because p is less than 1. So you see there's actually infinitely many p series for any particular value of p in the real numbers. But this is a very neat result in a direct application of the integral test, and it's a direct result that's going to be really, really important for us in the next lecture when we do our direct comparison theorem and our limit comparison theorem for series. So what I want to do right now is take a slight step back and actually discuss briefly the proof of the integral test, because I think it's very important to see this and to understand at least at a basic level why this is working, why the improper integral of the function f actually is telling you about the divergence and or divergence of the series. So to that end, what we're going to do is kind of split up both things that this theorem is saying, and that's into two parts: the convergence and the divergence. And I'll start with the divergence, and then I'll show the convergence. So part 1 will be divergence, and part 2 will be convergence. And to that end, what I've done here is just kind of plotted out the function f in red. This red curve is the function f. And I've also plotted out a number of different rectangles. And each one of these rectangles is defined in a very specific way. We have that the width of each of the rectangles is 1, because you're just going from 1 to 2 here, you're going from 2 to 3 here, and so on and so forth. So these rectangles are separated by the integers, and the heights of the rectangles correspond to the value of the function at the starting point of each one of the rectangles. So at 1, it's f of 1. At 2, this height right here is f of 2, and so on and so forth. And because of the definition of the terms in this series, in terms of this function f, that means that the height of this rectangle is a1, the height of this rectangle is a2, the height of this rectangle is a3, a4, and so on and so forth. But because the bases of each one of these rectangles has a width of 1, that means that the area of each one of these rectangles is also this corresponding value. So the area of this rectangle is a1, the area of this rectangle right here is a2, the area of this rectangle, the third rectangle, is a3, the area of the fourth rectangle is a4, and so on and so forth. And this is very, very nice because this allows us to directly set up an inequality, specifically the sum from k equals 1 to n of these areas of ak, of each one of these values of k. This will always be greater than the integral of the function f from 1 to n plus 1. So this is an inequality that's essentially at the heart of this proof right here. So this summation of all these rectangles will always be greater than or equal to this improper integral. And this is very clearly seen here from this picture. And all we need to do is take the limit as n goes to infinity to get that the improper integral from 1 to infinity of the function f of x dx will always be less than or equal to the infinite sum from k equals 1 to infinity of the terms ak. So just imagine this n right here going to positive infinity. And we now have that then if the improper integral diverges, or the area under the function f of x diverges, then the sum, this infinite sum, is also forced to diverge. Because we can think of the area under the function as this, I'll shade it in pink right here, it's all of this area right here. So basically, if this area blows up to positive infinity as n goes to infinity, then it's forcing the sum of all of these rectangles, which is also an area, to blow up to positive infinity as well. So this gives us the connection between the divergence of this improper integral and the divergence of the series, and concludes part 1 of this theorem, or this test. For part 2 of showing this theorem, this is the part where if this improper integral converges, then the series must also converge. We do pretty much the exact same procedure here. We say, okay, we're going to draw the function itself from, in this case, from 1 to n plus 1. And what I'm going to do is kind of take all of these rectangles right here we had from before and just shift every rectangle back by one rectangle. So in this case, we have then that the areas of all these rectangles. This area is A1, this area is A2, this area is A3, this area is A4, and so on and so forth for all of these areas. But the idea now is we want to create an inequality that makes sense, and we can kind of visually see from this picture. And sure enough, in this case now, what we want to do is look at a comparison of the following form. Look at the sum from k equals 1 to n of all of these AKs. The sum A1 plus A2 plus A3 all the way up to AN, just like we did up here, right? This goes all the way up to AN. So the sum of all these areas is going to be less than or equal to the improper integral of this function from 1 to n plus the area under this first rectangle A1, right? Because the improper integral of this function from 1 to n of f of x is going to be all of the area starting at 1 here all the way up to n. So it's all of this shaded area right here. And then we also have to add in that A1, that first term, which is all of this area right here. But so we know that this pink area right here, or the value of the area of this first rectangle, plus the improper integral, or the proper integral from 1 to n of this function f of x, this pink area right here, this is always going to be greater than or equal to the sum of each one of these sub-rectangles, because they're under this function. So just like before, we take the limit as n goes to positive infinity to get that. The summation from 1 to infinity of ak must always be less than or equal to a1 plus the improper integral from 1 to infinity of the function f of x dx. And this concludes the proof of the second part of this theorem, or this test, because basically now we have that, well, a1 is always going to be a finite term, and if this improper integral right here converges, or is a finite value, what we have then is that this infinite series also has to be a finite value, and so if this improper integral converges, then the series itself must also converge. And this is it. These part 1 and part 2 is just kind of to show both of the results of the integral test. I think it shows it in a very visual, nice, geometric way. So moving on to the final part of the lecture, what I want to do is write down a very, very important result from this integral test. This has to do with approximating the exact value of a convergent series. And I mentioned a couple times that in general, finding the value of an infinite series, what it converges to, is very difficult. And actually, some of the more advanced methods require much more advanced mathematics than we'll be going over in this class. So for certain types of series, we won't be going through and showing how to find the exact value of that convergent series, but a very useful tool is to estimate the value of the series, what it converges to, and get a good idea of how well that estimation is. And this is one of the things that we can directly do with this integral test. So in general, we'll assume that we have a convergent series and that this convergent series converges to S, where S is exactly this summation from k equals 1 to infinity of AK. If we truncate this series, so we only sum up the first n terms of this series, consider the nth partial sum, Sn. This is equal to the summation from k equals 1 to n of AK. And typically in practice, this is what we can calculate using a computer or using just by hand. So we call Rn the remainder, the nth remainder. This is exactly S minus Sn, which is a new infinite series that starts at k equals n plus 1 and goes to infinity. And as long as the infinite series of AKs is convergent, this makes sense. So what we want to do is get a bound, an error bound, on this Rn. And it turns out that this Rn, the remainder, will always be bounded above by the improper integral from n to infinity of the function f of x, and it'll always be bounded below by the improper integral from n plus 1 to infinity of the function f of x. And this is the main result that we have for the remainder and it's important for me to emphasize, right, that this function f is the function that is determining these AKs, right? It's giving us these AKs explicitly, so each one of these AKs is equal to this function f of k. And we have the three conditions from before for applying the integral test, which is that f is continuous, f is positive, and f is decreasing. And what's neat here is that because Rn is equal to S minus Sn, this inequality is equivalent to saying that S, the actual sum, is bounded above by Sn, the nth partial sum, plus the improper integral from n to infinity of f of x, and it's bounded below by Sn plus the improper integral from n plus 1 to infinity of f of x. So what this is essentially giving us is a lower bound for the actual value of the sum and an upper bound for the actual value of the sum. Right? The actual value of the sum, this s, is the thing that in general is very difficult to calculate. But what this result is giving us is how well we can do approximating with just finitely many terms in the sum. And to justify this or prove this, we can go through directly and utilize the same two parts that we showed before. Specifically, from the image produced for part 1, we have that our finite approximation is the sum of the first n terms. And if we look at now the remainder rectangles, so all of the rectangles from n plus 1 to positive infinity, you can see that these rectangles are overestimating or going over the value of the function. So the area under the function is this pink area that I'm shading right here. And it should be very clear that the remainder, Rn, the sum of an plus 1 plus an plus 2 plus an plus 3 all the way to infinity, is bounded below by the improper integral from n plus 1 to infinity of f of x dx, which is the pink area that I've shaded right here. And furthermore, if we look at the part 2 image from the proof of the integral theorem that I showed before, and we consider these green rectangles, which again is the nth partial sum when you add all of these areas together, we're seeing that the remainder here in this picture, all of these rectangles are underneath the function. So the remainder Rn, the sum of the rectangle an plus 1 plus an plus 2 plus an plus 3 all the way to infinity, will be less than or equal to the integral from n to infinity of f of x dx. And there you have it. This proves this remainder theorem. Specifically because the improper integral from n to infinity, or all of this area right here that I'm shading in pink, is a larger value than the sum of the areas of all of these rectangles from part 2. So this pink area right here is a larger value than the sum of all these rectangles. So what I want to do is go over an example of this theorem, both, we'll say, applying the integral test and also going through and using this remainder estimation theorem. So let's consider the series from 1 to infinity from k from 1 to infinity of 1 over 1 plus k squared. The function that is generating this series, or generating the AKs in this series, is the function 1 over 1 plus k squared, or f of x equal to 1 over 1 plus x squared. The improper integral of this function from 1 to infinity was shown in the previous lecture to be pi over 4. So then, by the integral test, the series for S converges. It converges because the improper integral of this function, which is positive, continuous, and decreasing, converges. Just because it converges, though, we do not necessarily know what it converges to. The integral test just tells us that because this improper integral converges, the infinite series must also converge. However, we can use our remainder theorem, and in this case, the remainder theorem is going to give us the following. Because the series converges, we're going to have that the remainder term, Rn, is going to be less than or equal to the integral from n to infinity of the function 1 over 1 plus x squared, and the remainder will also be greater than or equal to the integral from n plus 1 to infinity of 1 over 1 plus x squared, both of which can be evaluated and yield that this remainder will be less than or equal to 1/2 pi minus 2 times arctan of n, which is this improper integral, and the remainder will be greater than or equal to 1/2 pi minus 2 times arctangent of n plus 1 for any value n. Which is very, very neat. Equivalently, this means that the actual value of the sum will be between the nth partial sum of the sum plus this error term. That's the upper bound for the actual value of the sum, and the lower bound for the actual value of the sum will be the nth partial sum minus this error term. So, practically speaking, let's just say we take the first 5 sums in the partial sum. So we calculate S5, which is going to be the sum of these first 5 terms, which will be 1 over 1 plus 1 squared plus 1 over 1 plus 2 squared plus 1 over 1 plus 3 squared up to 1 over 1 plus 5 squared. Which has a value of 1,983 divided by 2,210. So this value of S5 is the first 5 terms in this sum, which is an approximation to the actual value of the sum. And specifically, this actual value of the sum is going to be between this S5, which is 1,983 over 2,210, plus the error term, which is 1/2 pi minus 2 times arctan of 5, and it's going to be bounded below by this 5th partial sum minus 1/2 pi minus 2 times arctangent of n plus 1, which is 6. And this lower bound, if we find the decimal approximation of it, ends up being about 1.06243. And the upper bound ends up being about 1.09468. So this tells us that the actual value of this infinite series is between 1.06 and 1.09. And while it's not always possible to go through and obtain the exact value of a given infinite series, for this series, we can go through and kind of check, see how this is doing. And sure enough, this series is going to converge exactly to the value 1/2 pi times e to the negative pi plus e to the pi over e to the pi minus e to the negative pi minus 1. Which is approximately equal to 1.07667. Which is, in fact, exactly between these two bounds. So this is, I think, a very neat way of approximating the actual value of an infinite series. I'm not going to get into where this exact value comes from because it's a relatively advanced method that will give us that. But this is just kind of a good example showing how to apply and use this theorem on the remainder from the integral test. So we expect these bounds to get smaller. So this bound should get larger and this bound should get smaller as we include more and more terms in the sum. Remember, this is only for an application of these bounds for the fifth term in the sum. As we increase n, we should get closer and closer and closer to the actual value of the sum. Whoops, and I just realized, I'm sorry, but I have a typo here. I calculated the values correctly, so all of the numbers here are correct. This should be plus, and this should be plus right here, because this right here is positive. This term is positive, which is directly matching what I wrote down before when I wrote down the formula. So this is the correct formula. I accidentally put a negative sign here, so I apologize about that. But the values that I computed are correct. I just checked them. So for example, if I were to repeat this process for n equals 10 instead of n equals 5, remember this result is for n equals 5. If I were to repeat this process for n equals 10, the approximation that I end up obtaining is approximately 1.07245 for a lower bound, and an approximation of 1.08146 for my upper bound. So this is very neat. And you expect these bounds to get better and better and better as you increase the number of terms in your sequence of partial sums. But that will conclude today's lecture. Thank you very much for tuning in. I hope you had a fantastic day and that you learned something.